You can see that if you follow an edge, the outside becomes the inside. According to topology, the Klein bottle has no volume. But if it has no volume, then what if we try to fill it with water? Well, if we just pour some water in it, then you can see that we're not going to be able to get the air out to get the water in. You're always getting blocked by trying to pour more in here. But I have a better way to fill a Klein bottle. I'm going to stick it in my vacuum chamber and suck out all the air. When I let the pressure back in, it will force the water up into the void in the bottle. Okay, turn it on. 3, 2, 1. So it's immediately bubbling because the air is expanding from the Klein bottle coming out the bottom. We're trying to get the inside of the Klein bottle to be as rarefied as possible. Okay, let in the air and it should suck right up into it. Here we go. Whoa, it's already going in. That is awesome. Fill it up. Didn't quite fill it all the way up. Okay, now we're taking this smaller volume of air and rarefying it again. Okay, let's do it again. A fully filled Klein bottle. Now at this point you may be asking why I would say that the Klein bottle has no volume. In order to have a volume, you have to divide the inside world from the outside world. For example, this sphere has a volume. There's a world outside the ball and a world inside the ball. And no matter how I stretch or manipulate the shape, there will always be a volume to it. But let's look at the Klein bottle. There's no fine line or edge to divide it into an inside or an outside. This problem with shapes having a volume was first realized in 2 dimensions by the mathematician Camille Jordan. He realized that there's no rigorous mathematical proof to tell the difference between a curve that encloses an area like this one or a curve that doesn't like this one. We can look at these 2 lines and instantly know they're different because there's one that encloses an area and one that doesn't. It seems obvious, but in order to prove it, this is what it takes. Mathematical papers use something called a lemma. A lemma is an intermediate proof that will be needed later to prove what they're trying to ultimately prove. This paper publishes the proof of the Jordan curve theorem. It shows lemma 1, lemma 2, lemma 3, then lemma 4, and then it finally gets to the actual proof. This is all to prove what we can instantly see with our eyes. So sometimes things are obvious to our eyes that isn't obvious in mathematics. But some interesting results happen once you start to understand these curves. For example, a simple closed curve like this one means that if you draw a point inside the curve, no matter how it moves or stretches the shape, it can't get out. Now for this example, it's easy to see that the point is inside the closed curve. But what about this closed curve? Is the point inside or outside this curve? Well, since we now understand these curves, there's some rules that we can follow. If you draw a line between the point of interest and another point that we know is outside the curve, then you can just count how many times it crosses the curved lines. And if it crosses it an even number of times, it's on the outside. If it crosses it an odd number of times, it's on the inside. Now back to our Klein bottle. From the start, notice that I called this a physical Klein bottle. That's because a true Klein bottle doesn't actually exist because it needs 4 dimensions to be a real Klein bottle. This is the self-intersecting Klein bottle in 4D, seeing 3D slices of it. And this is a non-intersecting Klein bottle. We have an extra dimension so it can move around itself so it doesn't have to self-intersect. So a true Klein bottle can only really exist in 4 dimensions. So in 3 dimensions, a Klein bottle is just a really fancy cup that you need a vacuum chamber to easily fill up.